Let's work through some examples using implicit differentiation. So in this example, we're looking for dy dx, given the equation x cubed times sine y plus y is equal to 4x plus 3. So if we wanted to find the derivative of this equation, we'd first start off by taking the derivative of both sides. So let's start by taking the derivative of the left side, the terms x cubed sine y plus y, and also the derivative of the right side. And I'm going to go through and rewrite our derivative term by term. So our first term, we have the derivative of x cubed sine y plus the derivative of y, and that's equal to the derivative of 4x plus the derivative of 3. Now looking at our derivative this way, we can see where each rule is going to apply. For example, anywhere the variable y shows up, we know we're going to need the chain rule. Anywhere we see a product between two functions, we know we're going to need the product rule. And then anything that's just terms of x or constants, for example, we would use our other shortcut derivative rules. So when we're looking at the right side of the equation, for example, the derivative of 4x, that's just using the standard power rule. So that looks like 4 times 1, because the derivative of x is just 1. And then when we take the derivative of 3, that's a constant, so that derivative is equal to 0. So the right-hand side of our equation is actually just equal to 4. So let's go ahead and rewrite that to clean things up a little bit. So I'm just bringing down the terms on the left side. We haven't taken those derivatives at all. And then we're rewriting the right-hand side equal to 4, since we took the derivatives on that side already. Now applying our product rule to this first term, the x cubed times sine y, I'm going to write that out step by step. So derivative of the first function, that's x cubed, multiply the second function, sine y, plus our first function times the derivative of our second function. This is going to help us with mapping out where we need each rule. The derivative of x cubed, that's just the power rule. That becomes 3x squared. We'll bring down our sine y multiplier. And then when we look at the second derivative over here, the derivative of sine y, we have to remember that y is a function of x. Which really means we're going to use the chain rule. So when we take the derivative of sine y with respect to x, we're really taking the derivative with respect to y first, and then we're multiplying by dy dx. We know the derivative of sine is cosine, so we have cosine y and then times dy dx. So cosine y times dy dx is going to replace our derivative factor here, and we're still multiplying that by x cubed. So this will look like x cubed times cosine y times dy dx. And that's just for that first term, the derivative of the product. So when we copy down our equation again in a second, we are going to replace that first derivative, x cubed sine y, with what we have in this green box. So we've got 3x squared sine y plus x cubed cosine y dy dx. We also had the plus derivative of y term left to take care of, and we had that was all equal to 4. Taking the derivative, oh, I copied that down wrong, damn it. Plus d dx of y equals 4. So we have one derivative left to take, and since that's the derivative of y with respect to x, we do need the chain rule again, so we'll take the derivative of y with respect to y, multiply by dy dx. And that simplifies to just be 1 times dy dx. All right, we finished all of the derivatives in step 1, so let's rewrite our equation now that we've taken the derivatives so that we can begin step 2, which is solving for the dy dx term. Now let's take a second and point out where the dy dx terms are. So we have one here, we have one here, and since there's more than one, we'll need to factor them out. Let's first move everything over to the right-hand side of the equation that doesn't have the dy dx term in it. So let's go ahead and subtract off this 3x squared times sine y, which just moves it over to the right-hand side. Eliminating it from the left-hand side. So now we have x cubed cosine y times dy dx plus dy dx is equal to 4 minus 3x squared sine y. And because both terms on the left-hand side have that dy dx factor in them, we're going to factor it off. That way we can write dy dx by itself. So we'll write dy dx times everything that's left after factoring. So pulling off the dy dx from this first term, we have x cubed cosine y remaining. And then when we pull the dy dx off of the second term, it just leaves behind a 1. And this is still equal to 4 minus 3x squared sine y. We haven't done anything to the right-hand side again. Now that we have dy dx isolated, we can divide off what's multiplying to it. On both sides of our equation. So that we have dy dx all by itself on the left-hand side equal to 4 minus 3x squared sine y, all divided by x cubed cosine y plus 1. And that's our final answer. Let's try another example. This time we're going to look for a second order derivative. And we've actually already taken the derivative of this equation in the previous video. But let's do it again just for good practice. So take the derivative of the left side. And take the derivative of the right side. On the left, the derivative of x squared just becomes 2x. The derivative of y squared with respect to x, that becomes 2y times dy dx. And on the right-hand side, derivative of 25, that's equal to 0. We want to isolate the dy dx, so we'll subtract 2x from both sides. so that we have 2y times dy dx is equal to negative 2x. Then we'll divide off the 2y from both sides, so that we have dy dx is equal to negative 2x divided by 2y, and we can reduce the 2's for a final derivative of negative x divided by y. But that's only the first derivative. So dy dx is equal to negative xy, but if we look back at the original wording of the problem, it is asking for a second derivative, so we need to do it again. So we're going to continue this. We have dy dx is equal to negative x over y. And we're going to take the derivative of both sides. So again, derivative of the left and derivative of the right. On the left-hand side, we're taking the derivative of a derivative. That's exactly what a second derivative is. So we have the second derivative of y with respect to x. On the right-hand side, we have x divided by y. And since y is a function of x, we need the quotient rule. So remember the quotient rule, if you have a function f divided by g and you take the derivative of that, the pattern is take the derivative of the top function first, multiply that by the bottom function, subtract the top function times the derivative of the bottom function, and all of that is divided by the bottom function squared. Oh, I extended my division bar a little too far here. It should just be over here on the quotient rule. So we're going to apply that quotient rule to this negative x divided by y term. So we'll have the derivative of negative x times y minus negative x times the derivative of y, all divided by y squared. We've got two derivatives to take here. One of them is a term x with respect to x. The other derivative is a term with y with respect to x. So we need the chain rule on that one. So we'll take them one at a time. Let's copy down our second derivative notation. Taking that first derivative, negative x, that becomes negative 1, and that was multiplied by y. We have a double negative here minus a negative x, so let's write that as plus x times the derivative of y with respect to x. That just becomes dy dx, and all of that is divided by y squared. Now we know what dy dx is, so we're going to take that and plug it in right here. So recall that dy dx is equal to negative x over y. So we can pop that right into our second derivative equation here. And then we'd like to clean this up the best we can. So in the numerator, I have negative y plus x times negative x over y. We can multiply those two factors together to get negative x squared over y. But but then all of that's over y squared, and we don't like fractions inside of fractions, so let's get a common denominator in our numerator, multiplying that first term by y over y, so that we can add the terms together in our numerator. We'll have negative y squared minus x squared over y, but then that whole numerator is over the denominator y squared. And we can just combine our two denominators so that it becomes negative y squared minus x squared all over y cubed. And that'll be our final answer. So the second derivative of y with respect to x worked out to be negative y squared minus x squared all divided by y cubed. And this would be our final answer. Moving on to our next example, we're going to find the tangent line to a circle. So using that same equation that we've worked with a couple of times already, x squared plus y squared equals 25, this time we're going to find the equation of the tangent line to that curve at the point 3, negative 4. So remember, to find the equation of a tangent line, we need two things. First, we need the derivative, or the slope, at the point that we're given. And that is going to come from our first derivative. And then we also need the point slope equation. Our x1, y1, that's the point that they give us. So our x1 is 3, our y1 is negative 4. And we know what our derivative is. We've already done this a few times. So dy dx, hopefully remember, worked out to be negative x over y. And if we're looking to calculate the slope at the point 3, negative 4, we just need to plug in 3 for x, negative 4 for y. So our derivative, dy dx, at 3, negative 4, looks like negative 3 divided by negative 4, which simplifies to 3/4. So that's our slope. We will plug that into our m value. And then we plug x1 and y1 into their places in the point slope equation. So we'll end up with y minus negative 4, that's our y1 value, equals 3/4 times x minus 3, because that's our x1 value. And then we'll clean this up the best we can. Subtract 4 from both sides so that we can write our final answer as y equals 3/4 x. We've got to combine some fractions here, so let's do a little bit of scratch work. We have negative 9/4 minus 4, but 4 has a denominator of 1, so let's get a common denominator, multiply by 4 on top and bottom. So really we have 9 minus 16, which looks like negative 25 divided by 4. And that's our final answer. Another tangent line example. This time we're looking for the equation of a tangent line to the graph of 3y, not 3y. y cubed plus x cubed minus 3xy equals 0. So first thing we need to do is find the derivative so that we can use that to calculate our slope at the point 3/2, 3/2. So taking the derivative of both sides of our equation, we're taking the derivative of y cubed. We're also taking the derivative of x cubed. And finally, we're taking the derivative of 3xy. And on the right-hand side of the equation, just the derivative of 0. And let's just talk for a second about what each one of these derivatives is going to require. The derivative of y cubed with respect to x, that's going to need the chain rule. So we'll take the derivative with respect to y first, and then multiply by dy dx. The second one, that's just the power rule. We know that works out to be 3x squared. This third one, though, we have x times y. This one's going to require the product rule. We will need the derivative of 3x times y plus 3x times the derivative of y. Whoops, not the derivative with respect to y, the derivative with respect to x of y. There we go. So let's go ahead and do each of our derivatives on the left-hand side first, and then we'll pick up from there. So derivative of y cubed with respect to y, that just looks like 3y squared, but that is being multiplied by dy dx. And then we're adding to that our next term, which is 3x squared. And then we need our product rule. Notice that we have a subtraction. So I'm going to write the subtraction sign here with parentheses so that everything in my product rule is being subtracted. This first derivative, the derivative of 3x with respect to x, that's just 3, but it's being multiplied by y, so that turns into 3y. Next we have plus 3x times the derivative of y with respect to x. We're just going to write dy dx there. Close our parentheses, and then let's look at the right-hand side of our equation. It was the derivative of 0 with respect to x. And 0 is a constant, so the derivative of a constant is also 0. Now we've taken the derivative of both sides of the equation, so we're ready to isolate that dy dx term. Notice that it is showing up in two places. We've got to do a little bit of algebra to find how to isolate dy dx. First, we might want to distribute this negative into our parentheses so that we could isolate the terms involving dy dx. So let's go ahead and start with that. And then let's get rid of any term on the left-hand side that does not involve dy dx. So this positive 3x squared, for example, let's subtract that from both sides so that we can move it over to the right-hand side. And this minus 3y, let's add that to both sides so that we can get it over onto the right-hand side as well. Now we've eliminated everything on the left-hand side of the equation that does not involve dy dx. So now we can factor out the dy dx. And then in parentheses, write what's left behind from those terms. So that first term had a 3y squared. This other term had a minus 3x. And that's the only thing left on our left-hand side of the equation. But on our right-hand side, we now have a minus 3x squared and a positive 3y. I'm going to go ahead and write the positive term up front. There we go. So we're almost there. Our last step is to divide the factor off of the dy dx term. So we need to divide this group of parentheses here. The 3y squared minus 3x And that leaves our dy dx all by itself. Oops, almost forgot my square in the denominator. So this is the derivative, and if we plug in the point 3/2, 3/2, that will give us the slope at that point. So let's go ahead and do that next. So our derivative with 3/2, 3/2 plugged into it, we can write that notation to say that's what we're doing. That's going to look like 3 times y, where y is 3/2, minus 3 times x squared, where x squared is also 3/2. That's our numerator. And then we have 3 times y squared on bottom, minus 3 times x on bottom. And if we clean this up, that's going to look like 9/2 minus 27/2. Not 27/7, 27/2. There we go. And then on the denominator, we will have 27. Forgot to square my denominator. So if we multiply this out, we get 9/2 minus 27/4 divided by 27/4 minus 9/2. We are going to need a common denominator if we want to add these fractions together. Or what we can do is multiply the numerator up here by 2 negatives, send one of the negatives inside of the parentheses so that it looks like negative times negative 9/2 plus 27/4, which we can write as this. And at this step, if we remember that anytime you divide a number by itself, it's equal to 1, we can see that 27/4 minus 9/2 divided by 27/4 minus 9/2, that's equal to 1, but we've got a minus sign here. So this will simplify to -1. If you want, you can plug that into a calculator, find that it simplifies to -1, but sometimes it's useful to see these handy-dandy little tricks that allow us to calculate things quickly without using a calculator or finding a common denominator. Okay, so we have our slope, and that's the only thing that we needed to find the equation of the tangent line. Y minus y1 equals our derivative at the point, so that was -1 times x minus x1. Oops, but x1 we know is equal to 3/2. So we'll clean that up. We get y equals -x plus 3/2 minus 3/2. Plugging our slope and our point into our point slope formula, we get y minus 3/2 equals -1 times x minus 3/2. Multiplying out on the right hand side, we have -x plus 3/2. We want y by itself, so let's add 3/2 to both sides of our equation to get our final answer of y equals -x plus 6/2, or 3. So the equation of our tangent line to that original equation looks like y equals -x plus 3.